Alright, well, for Bio 2, this is your first official lab with me. Again, there are going to be, I'm trying to remember how many, I think 12 in total that I have posted. Each one, understand, is worth 20 points. No matter what, the lab is always out of 20 points, whatever score you get back. And I change the amount of points per lab, questions and things you do as per how large the lab is, so it's all done in uniformly. For the first one, though, there is no real lab where you actually have to do anything. Basically what it is, it's going to be as long as you have a Wi-Fi hookup or internet, be able to get to it, you'll be able to handle this very, hopefully, very easily. Alright, so the lab is on what's called phylogenetics. So if you go on Canvas, it'll say phylogenetics assessment tool all the way at the bottom of module 1. That's the first page. Okay. Now, when you go through it, it's going to go through all of what phylogenetics is, what's a cladogram, and how it's basically more or less set up. That's what I went over with you with the PowerPoint in the third chapter, phylogenetics. All right. So, to get down to brass tacks of what you got to do for me. Now, first off, there's going to be a website you're going to have to go to. It's called NCBI, the National Centers for Bioinformation, Bioinformatics. So basically, if you just go on Google and type in the acronym NCBI, it'll be the first thing that pops up. The National Center for Bioinformatics is also the house for the National Library of Medicine. It's also the house for the Centers for Disease Control. So basically, anything medical, anything science in the U.S., this is your go-to spot. It's governmentally run, so keep in mind, as long as the government is open, you have access. However, if they go on strike or other things, then you have no access or limited. But right now, again, knock on wood, everything's going okay, so you can just get the lab done. Just as a reference for future classes, if you have to do anything dealing with medical, dealing anything with DNA, RNA, protein, this is the place to go to. And the great thing about it has links to go all over the world to anything you can possibly imagine. And because it's government run, it's 100% free. So your tax dollars pay for it, so we're going to use it. All right, because I'm a dork, it's my favorite site ever to go to because it's basically my playground. All right, so if you look in the lab, the digital lab thing, all the way at the end, there are going to be 2 pages. The first page is going to look like this, which is going to say, well, what's the phylogenetic analysis between organism A to organism B, organism A to organism C, A to D. Now notice that when we do our phylogenetic comparisons, if you remember from the third chapter, we always have to have something called an outgroup. The outgroup is going to be the group with which means we have a comparison with all others. It's the control, essentially. For our lab analysis, our outgroup will be critter A. Okay, we don't know who critter A is. We're just going to see how many differences there are between the sequence of critter A to that of critter B. A to C, A to D, A to E, A to F. And those are the numbers you put in here. Okay, so you put the number of differences. I'm going to walk you through this. Okay, now, next thing you're going to do is, based upon these differences, you would set up a cladogram down here, which again, I'm going to walk you through. My suggestion, highly big suggestion, I would do it in pencil, because when you do it in pen, it makes a big, huge mess. So therefore, you're probably going to print it out and be able to do it by hand, because otherwise it's not going to come out too well. The rest of it basically is going to be a bunch of point, click, get the information, point, click, get more information, okay? But the more of the nuts and bolts of this is going to be these 2 things here, and that's the most important thing I need to walk you through. The rest of it's going to be, again, like I said, copy, paste, what is it, copy, paste, what is it, which, again, I'm going to walk you through. All right, so what we're looking at are going to be amino acid sequences specifically for the enzyme called amylase. Amylase is an enzyme found in, well, most living organisms, because amylase is an enzyme which breaks down carbohydrates. You have amylase in your salivary glands, you have amylase in your pancreas. So basically, if you are a creature, an animal pretty much that breaks down carbohydrates, you better damn well have an amylase gene somewhere in you. Okay? Now, on here, if you look now, in this box, it has the amino acid sequences for different sequences of amylase from different creatures, okay? Therefore, we have critter A through F, don't know who they are, And these single letter designations specifically it's a mnemonic in biochemistry where you are given an amino acid and it gets a one-letter abbreviation. That way you don't have to write out lysine, glycine, methionine. You can just put the one letter and make it easy, okay? If you're that concerned about what the individual letters mean, no problem. When I wrote the lab, those are all the abbreviations for the amino acids on the previous. It's going to be unimportant for you, but in case you're inquiring, then there you go. All right. So now again, what you need to do for that first table, you're going to take sequence A, critter A. Do not include the letter A. That's critter A. Where it's bolded from that point on, that's where you're going to compare the positions. So if you were to look at this, you want to zoom in on this. If I'm going to compare organism A to B, notice the first letter in organism A's amino acid is N. In B, it's T. Well, that's a miss. You would count that as 1, a miss. You go to the next one, NT, another miss. That's 2 misses. ND, that's 3 misses. Then GG, that's the same. That one, that one's the same. So therefore, we don't count it. You only count misses. How many differences there are. If you notice too, when you look at this, in the middle of a sequence, you can have a dash. In biochemistry, that dash is a mnemonic, which means there's a potential of having more than one amino acid at that position. For you all to do this analysis, if there's a dash in the sequence, but only a one-letter designation in the sequence you're comparing it to at that position, it's a miss. If there's a dash and in the sequence at the same spot, there's a dash, that's the same. Okay, so count it that way. Also, when you look at the sequence, notice it's pretty long, but in the middle, well, not in the middle, about 1/3 down, it goes ... What is that? That's me being kind to you. Why? Because this amino acid sequence is huge, all right? So basically, ... means there's a bunch of stuff in the middle that I'm skipping over to make it easier for you. So this is the beginning part of the protein. This is the end part of the protein. The middle part I'm skipping over because you're going to get the point just by doing the beginning and the end, all right? So whenever you see in the lab where it says what is the first half of the sequence, that's before ... When it says the second half, that's after ... All right? Now notice something here, guys. Before ... the sequence is a lot shorter. After ... it's a lot longer. Think mathematically, think statistically. Whenever you're doing any sort of statistics, whenever you're doing any sort of number crunching, does your data become more or less valid or have a stronger argument for it or less source of error when you have more or less data? Well, the more data you have, your error should decrease because you have more data. Make sense? When you have less data, that means that you throw in more wild chances of error, outliers to come into your data plot. All right? So keep that in mind. All right, so first thing you need to do is then fill in that table on the first part of the answer sheets, the last 2 pages of the lab, where I have the table compare A to B, A to C, A to D, and then basically you're just going to fill the numbers, okay? Now, the whole idea here is this. Based upon phylogenetics and molecular cladistics, the idea is this. You can look at evolution on a couple different levels, where evolution can be looking at different types of morphologies, like, oh, do you have wings? Don't you have wings? Can you have gills? Do you have lungs? How do you move blood around your body? Hemoglobins. Anything can be a trait or a character, down to the molecular level of amino acid sequences. So right now I'm giving you a bunch of critters, and you don't know who any of them are. All you're looking at is a bunch of letters in their amino acid sequences. What we're now going to do is, based upon the differences that you saw between A to B, A to C, A to D, now understand the comparison is always toward A. That's our outgroup. We're not comparing B to C, we're not comparing D to E, it's always compared to A. That is the control, okay? That's going to be crucial later on. Now, what we're seeing then is, the idea is, the more differences 2 creatures have, the more distantly related they should be evolutionarily. Well, is that the case even on a molecular level? Yes, 100%, same thing, okay? So we're going to figure this out as we go through it. All right, so what you would do then is, again, you would fill in that table. So let's just say that was your table, comparing A to B, Okay, well, obviously, here, real simple. One of the first things I have up there is if you compare the sequence of A to A, how many differences should there be? 0. Right. That's why it's going to be our outgroup, our comparison. Now let's just say this isn't the correct data. I'm just throwing out numbers. Let's say when you compared the sequence of A to B, you discovered there were 8 differences, okay? Let's say when you compared A to C, you had, let's see, we'll say 15 differences. Let's say when you compared A to D, you had 17 differences. Again, just throwing numbers out there is all I'm doing. Now, in the lab, when you read it, what you have to understand is, on a statistical level, what would be a significant number of differences between A to B? If it's a significant number of differences, if you look at a cladogram, cladograms, if you looked at the 3rd chapter, it looks like a tree with branches on it coming off. Well, these little end parts where you have are called nodes. Nodes are where you're saying it's significantly different from something else, therefore you're on your own branch. You have to have a justification as to why you made a new branch or why you made a node, okay? These number differences are going to be our justification for the node. But I have to give you something to give you a means of comparison. So in the lab, if you have 5 or more differences, that statistically is going to be significant enough to warrant your own branch, okay? So follow. If we start to plot the cladogram, this is 0 differences going all the way up to 45 differences, okay? Obviously, we're only going to need up to 17 here for this example. All right, so let me use a different color. So, if we compare A to A, how many differences were there? 0. Well, that's easy. You put a big old dot at 0. You call it organism A. And then in parentheses, you have to tell me, well, why is it there? Because in parentheses, there were 0 differences. That's why it's there. Okay, great. Next creature you look at, notice, was B. B has 8 differences in sequence compared to A. Well, is 8 5 or greater? Yeah. So therefore, it has to be its own branch based upon what we said earlier. So we come back on the number line to where you would have 8 differences. You would then put a big letter B, critter B, and then you would tell me it has 8 differences. Because it has more than 5 or more, it has to be its own branch. So just any angle you want to, you make a line back to the origin. That's a branch. Cladograms, understand when you make cladograms, they don't start off vertical. You draw them horizontally because it's easier, and then when you go to print it, you bring them upright, and it's easier to do. It's just easier when you do it horizontally. All right, now, C has 15 differences. Okay, 15 obviously is 5 or more differences. Okay, now the next question we have to ask ourselves is, between B and C, are there 5 or more differences in those two? Well, notice that B has 8 and C has 15. Even without doing a direct comparison, that's well over 5 differences. It has to be on its own, okay? So therefore, because C is on its own, you'd come back to 15, you'd put a dot, put C, 15. Because it is 5 or greater compared to A, and 5 or greater compared to B, it's going to have its own line. Cool? This is now where we start to get funky, all right? Because if you don't know me by now, I like to turn things a little bit. All right, now look, organism D has 17 differences. We can all agree that 17 is far greater than 5. So definitely, when we compare A to D, it's on its own on its own island. Question is this: D has 17, C has 15, but that's only comparing to A. What we now have to do, what you would have to do, is if the numbers are that close, you have to go back to the sequences in there and you have to compare C sequence to D sequence, because this is only to A. Well, let's just say when you compared C to D. When you compared C to D and you found out, let's say there were 7 differences. Well, if I compared C to D and there were 7 differences, that's 5 or greater. Well, that tells me, hell, that's its own branch. So in that case, let's say that there were 7 differences. That means that the graph, still understand, is comparing to A. So we have to draw it with respect to A. We'd come back on the number line to 17. You'd put a D, and you would say there were 17 differences. And then you'd make its own line. Understand what the line is saying. D was significantly different from A, and because it's its own separate line than C, it's also significantly different than D, meaning 5 or more differences. Okay? Now, what if that's not the case? What if instead let's just say that D only had one difference from C. Well, 1 is less than 5. We can all agree 17 is still miles away from A, so that's definitely on its own. However, C and D say when you compare them only had one difference. Well, that's not a significant difference. That means they're kissing cousins type of thing. So what you would do in that case, you would use the line you drew for C. You come back to where there would be one difference. You would call that dot letter D and say one difference. And then you make this little tiny stinky line right there, a little branch coming off of it. What that's saying is this: C is significantly different from A. D is also significantly different from A because it's on C's line. However, because D is on the same line as C, they are not significantly different from one another. Okay? This is why we do it in pencil. Again, if you have questions, I'm in the chat room during class hours. Just ask me, okay? If you want to do the numbers and figure it out and say, well, are these the numbers or not, Mr. Bottesch? No problem. I'll tell you yes or no. I'll tell you what the numbers are. I want you to get this down, at least have the idea of how to do it, okay? Now, for the second part of the lab then, that's where you're going to have to, cut, paste, and then figure out whether or not what the creatures are, okay? So, do me a favor, hit pause. All right, so now we want to do the second part of the lab. Second part of the lab says, what's the name of the organism for the first half of sequence A? What's the E value? What's the second best match? What's the E value? What would be the second, what was the organism from the second half, meaning after ... for A, the first hit, the second hit, and what's the E value? What's an E value is it's the error, meaning what's the chance somebody's at NCBI and they have hundreds of millions of these possibilities, and they close their eye and they put down on their finger and they said, oh, well, that sequence is a fruit fly. Yeah, the smaller the error is, the more chance that it's a true result. And remember, the more data you give, the less of an error there should be. All right, so over here. So notice what I did is that's NCBI, okay? So it's www, NCBI, NLM, NIH. That's the National Centers for Bioinformatics, National Library of Medicine, and National Institutes of Health. I was incorrect when I said Center for Disease Control. They got their own thing. All right, so when you're on here, what you want to do is you want to come over to this area that says BLAST, B-L-A-S-T. BLAST stands for Basic Loci Alignment Assessment Tool. All right, now notice when we come here, when we go to BLAST, there are two types of BLAST, nucleotide and protein. In the lab, I gave you an amino acid sequence, so we got to go to protein. Can't use nucleotides. I didn't give you A, T, G's, and C's. So we click on Protein BLAST. What you now get is a query box. This is now why I gave you a digital version. I'm not trying to grade you on your typing ability, the letters in order correctly on the site. So all you got to do, come back to your lab. For critter A, do not include the A. Before ... you have these letters here. Include the dash. Okay? So I'm going to copy it. I'm going to go to the site, and I'm just going to paste it. Drop it on. All right? Now, before we hit BLAST, BLAST essentially means go. All right? We have to come down here. It's going to say database. What database do you want to use? What should come up by default is non-redundant protein sequences. Why? Because there's different databases in here. There's a Homo sapien database. There's a Drosophila melanogaster. There's Rattus norvegicus. All sorts of creatures are on here. But we don't know what the hell that is. So we want to look at everybody. But we don't want it to be redundant, meaning once you find a match, don't give me the same thing a million times in a row. Go to the next one, the next best one. All right, so here we go. As long as it says NR, non-redundant, we're going to come on down here, and then we're going to hit the little BLAST. And then we wait. Now, depending on how many individuals are on it at this time, depends upon how long this is going to take. So basically, at this time, this is whenever you walk, but it'll keep reloading until it finds the answer that you want. So basically, you just, go make a sandwich, go bathroom, do something. Stare out the window. Don't. All right, so I'll go back over here. We're just waiting for it to refresh.
Stare out the window.
Sure. All right, so here we go. What we now do is we come on down, and it tells you the creatures that it nailed. Notice these are in order, meaning best hit, next best, next best, next best. All right, so if we look at this one. This one says the gene they found for that first part was pancreatic alpha amylase from tupaiacinesis. Pancreatic amylase. I told you this is an amylase. Woohoo! We're in the ballpark. All right. Now, notice the first thing it says here, though, is what is the name of the organism for the first half? The best hit. That would be tupaiacinesis. Whoops, the one that one, tupaiacinesis. Then it asks you, what is the E value? The E values are over here. So you go to the first, come all the way over to the E value, and it's 1 times 10 to the negative 11th. Meaning the chance that by the chance somebody said, oh, tupaiacinesis is less than 1 in 1.000000001. In other words, no. Okay? Now, whenever you do your lab, I'd like you to use the scientific genus and species. However, I'd also like you to put next to it the common name. I'm quite confident you don't know what the hell tupaiacinesis is. So let's go find out. All you do is you go to that and you click on it. Click on it. Then it'll tell you pancreatic alpha amylase tupaiacinesis. Then it says sequence ID. That is called an extension number. It's kind of like a Dewey Decimal System for organisms on this site. All you do is click on that link, and you come up with the sequence. The first time it was printed, it'll tell you who printed it, where it was printed, and everything else. If you ever take my class biotechnology, we go a lot more further into this. But notice, source, tupaiacinesis, Chinese tree shrew. If you don't know what a shrew is, it's a small mammal about the size of your pinky. It's one of the more primitive types of mammals. Basically has to eat roughly anywhere from 5 to 7 times its body weight in insects a day just to stay alive. So it's a very primitive primate. So it's a mammal, okay? Now, let's now go back. And if you notice then, I ask you what's the second best hit? Well, that would be this one down here. And then you'd get the error, and then you'd tell me what that creature was. All right, so now for the other one, for the next question, let's ask you, well, what was the identification for the second half of after ... I don't want to reset the whole darn thing. There we go. Oops, too far. All right, so National Center for Bioinformation, a blast, protein blast, protein blast. There we go. And now I'm going to come back to my lab. I did the first half. Now let's do it after ... Notice more letters, more data. What should happen is that error value should drop like a stone. All I do now is I paste that in there. It already says non-redundant. We're all good to go. And then you hit blast. And then we play the waiting game again. Stare out the window again. Kick a squirrel. Do something, who knows. Feed the dog. Wash a dish. Because you've been in quarantine, maybe brush your teeth, put on some deodorant,
God.
Something like that.
Take a shower.
All right, so notice, same thing. When it comes up now, the first hit is Homo sapien. It says HCG. HCG is human chorionic gonadotropin. It just so happens that that part of the sequence for HCG, which is what a woman gets positive for pregnancy in a home pregnancy test, that it shares a similarity with actually amylase. Now notice, I'm assuming you know what Homo sapien is. That is modern day human. If we come down to the error over here, the error is 1 times 10 to the negative 23rd. More data, the error drops like a stone, meaning there's no chance in hell it's not what it is. Then again, if you don't know what Homo sapien is, again, same thing. You would click on it, and then you'd click on the extension number, and the same deal as last time. All right? Now, last thing I'm going to show you is what if we take the whole kit and caboodle, everything. First part, ... and second part. What do we get? In other words, the most data that I can give you to tell you what this critter is. All right? So notice the first half said it was a shrew, a mammal.
Second half said it was Homo sapien, a human. But the first half said pancreatic amylase, second half said HCG. Well, what the hell is this? So, if we give it all the information, I'm just going to get rid of all that, come back to my lab, and except for the A, sample A, everything including the ... I'm going to copy it, and I'm going to paste it. And then, again, non-redundant sequences, NR for the database, and, oops, didn't go too far down, and blast. Remember, put the deodorant on, change the clothes.
Take a shower.
You don't have time to take a shower. Sponge bath, maybe. Wash your face. Clean the mirror from all the little spit you had from brushing your teeth too close to the mirror. Stuff like that.
Oddly specific.
Well,
Well.
I see things. Just say. All right, so come on down. Now we have the most data. Notice, lo and behold, AMAY2A. That's amylase 2A isoform. That's the enzyme. And we got Pongo albilei. Come on down. The E value is 2 times 10 to the negative 29th, even lower, which means, again, more information. If you don't know what Pongo is, we go to that. We go to the extension number. And what we find out is Pongo is the genus specifically for simians. In this case, it's the Sumatran orangutan. Okay? It's basically one of your cousins in the world of genetics and phylogenetics. Okay? So, with that then, that would do all this here. All right? Now, when we flip the page, what I need you to now do is figure out who critter B, C, D, E, and F are. In this case now, again, you'd go back to the data and you would do the whole thing for B, not the first and second half, just the whole thing. B, whole thing C, whole thing D, do the same thing. Figure out who they are. Why? Because you drew a cladogram based upon a bunch of letters. I want you to know who the critters are now and to go, now that I know who these critters are, does my diagram based upon amino acids and letters, from my limited knowledge of the animal kingdom, does it make sense now that I know who the critters are? Okay, so up here then I need the genus, species, and also common name. Question number 7, if you were paying attention, I already answered for you. And number 8 is the question I just said a second ago. Now that we know who critters A, B, C, D, E, F are, and when you go to your cladogram that you drew on the other page, do they make sense? In short, they should make sense, okay? All right, so that is the lab that's going to be for phylogenetics. Again, the posted dates and the announcements, and that's what I need it by. If you have it done before then, cool, turn it in, no problem, no harm, no foul. All right, but I need it by the due date, okay? All right, so I'll see you next for the pre-lab for prokaryote.